recording. All right, so everything is being recorded. The sound is good. The screen is good. All right. So I was sending an announcement, but I don't see it here. So I was probably in the process of typing it. Okay, that's fine. Um, so what I was sending is a way to find the exam for today. So if you go to the shared drive here, which is linked from the like the first one or two modules of in Canvas, go to the shared folder. It will be over there. So let me just navigate to the shared folder from here, because from my other classes, I found it's really difficult to. So you go to X2 in the share folder, you will find the exam from last semester, which is spring 2024. So can you guys find that from the share folder? Yes. Okay. So you don't have to go there. Okay. If you cannot find it, or if you just kind of focus on the projector, that's fine too. But if you can go there, that means you can actually view the document as I put in the answers into the document. Um, you can consider one of two things. You can either just kind of follow along, use one browser to follow along, and then use another one to take notes. So you can actually go to File, on your side. You don't see as many options because you don't own this file, but you can go to Make a Copy. Then you can just go ahead and put in whatever comment you want to put in your version of that file. Okay, so you got a few options that you can choose to do whatever you want. All right, so this is exam 2 from 2024 spring. The one that we are having on next Tuesday is going to be similar, okay, but not exactly the same. So there are two things that are definitely going to be different. Is double or floating point number representation is not in yours, okay, because we got that in the first exam already, okay. But then we're missing one question. So I'm going to throw in a third question, which we'll also talk about today. So I'm not going to leave you guys stranded and go like, we have never seen this kind of question before. So we'll cover that one too. All right, so with that said, it is still open. Yes. Yes, I believe so. Yep, I'm recording. Yep. So, okay, it's good to double check. Thank you. Right. So it is still open book and open notes. Okay, so that means that you have about a week to put together all the material that you want to bring with you to the exam. Okay. You can print anything you want. Okay. You can also handwrite anything you want. You can bring any amount of your paper that you want to bring with you. The only restriction is no electronic devices other than a calculator. Is that okay? So does everybody understand the restrictions of what you can and what you cannot bring to the exam? Essentially the same as exam 1 and exam 2. I mean, the final exam will be the same as well. All right. So we are going to get started with the first two questions of what you already have. Okay, so I just pasted something earlier from, because I was looking into a Chromebook, for as a drawing tablet, because the other one that I have is not working. All right. So the first question is like this one, and I am going to edit a little bit because these are actually incorrect. So these are not NOR gates, SR latches. They're just regular SR latches. The most important point about the SR latches is the truth table is provided to you. So this part here is the truth table for the SR latch that you're working with. And in your exam, I may or may not give you the same kind of SR latch, so you have to pay attention to the comments that is provided here. If you have any questions, okay, if you see any contradicting kind of information like what I just erased, then come to me and ask me about it. Okay, it's perfectly okay for me to ask, for you guys to ask for clarification, or if you suspect something is wrong with the question, just come forward and talk to me. All right, so these are the components. The connectivity or the actual circuit is implied by the node numbers. Okay, so we'll get to that part next. There are 5 steps, okay, in this case, but you don't have to work from scratch. So that's the nice thing about this particular exam is, well, okay, the one in spring 2023, 24 is, the table is for the most part filled up already. Okay, you just have to focus on the columns that are not filled in. You are going to perform a NCPD trace. So do we need a kind of like a quick reintroduction of NCPD? Okay. So it is also described here. Let me see here. A change input pin should be indicated at the initial N0 of the step, which is already in the table. So the table is already pre-filled for the most part. Okay, so your job is to fill in the columns that are missing, as it is discussed here. Some columns are missing the values. So your job is to fill in those particular columns when they should be filled in. Let's see. If the value of an output port remains the same despite the update of at least one of the input ports of the device, leave the corresponding cell blank, which basically means, unless there is a change, don't put anything in the cell. Okay, which is the convention that we have already used in the lab that we already worked with. A step terminates if and only if no node as identified by a number is affected, indicating there are no changes to any input port of any device. The end of each step becomes the beginning of the next step. Each step should start with NC and end with a PD. Assume all ports to have unknown values initially. So basically, we know nothing about any one of the devices, including the input pins initially. They were all question marks. All right, so we are going to get started with this table. And I can zoom in a little bit because I think the default text size is a little bit on the small side. So now it should be more readable. Is that okay, or should I magnify one more time? This is good? Okay, all right. All right, so we're going to get started with this. So basically we have, J as a device, that's our SR latch. F is also an SR latch. D is also an SR latch. A is an AND gate. B is a port. H is a port. G is also a port. B and G particularly are input ports. So this one and this one are input ports, and that's the first step. And because this is an NC row, so that means anything that connects to node 1 should also get a 0. This is another node 1 over here. That's why this is also getting a 0. This is also a node 1. That's why it's also getting a 0. This is on node 0. Okay, so that's why everything on node 0 should also get a 0. The only other column corresponding to node 0 is this particular column, and that's why it is getting a 0. So are we good so far? Yes? Okay, so NC stands for node connectivity. In other words, we are looking at how things connected logically to the same node are getting updated because one of the points of that node has just changed. So are we good with that concept? Okay, all right. So the next row is a PD. PD stands for propagational delay. And what that means is, a device, okay, some devices, depending on, what the inputs are, the output can change as a result. So SR latch is one of those devices, a NAND gate is one of those devices, a regular AND gate is one of those devices, a NOT gate is one of those devices, and so on. The only devices that do not change the quote unquote output because of a change to the input are the input pins and the output pins. Okay, so input pins are basically input parameters. They allow us, to initiate or initialize the change to the circuit. That's the input. And then output pins are only useful for reflecting, what is the current state of something. So as a result, they are not devices. They do not have an input that can change the output. All right, so the way we figure out, the PD is to look at things that have changed in the previous NC row. If one of those is the input pin of something, then we are going to look at the corresponding output and go like, okay, should we make some changes to the output? So the R port of an SR latch is an input. So now we have to ask the question, if the R port of an SR latch is changed to a 0 without knowing anything about the S port, can we come to any conclusion about at least one of its two output ports? So the way we figure out the answer to this question is to go back and look at the truth table. This is our truth table. For the convenience of this discussion, I'm going to take a screenshot of the truth table of the SR latch, so that I can we can have visibility of this as we go through the trace. Okay, so it's just a convenience thing. You probably won't need something like this in your actual when you're answering your question. I need to move it. Okay, there we go. Alrighty, scroll down. All right. So now the question is, if I know nothing, okay, other than the R input port of an SR latch is now a 0, can we confirm anything about the output based on the truth table? And the answer is yes, okay, because this row, okay, and this row are both corresponding to when the R input port is a 0. Now, we cannot say anything about the Q port, okay, because the Q port also depends on the S port. But when we look at the NQ port, the output of NQ, as long as R is a 0, NQ is always going to be a 1. So that means, yes, we know for certain that the NQ port is going to be a 1 in this case, so we put a 1 over here. Is that okay? All right. So I'm going to italicize this one just so that it's easier for it. It stands out a little bit in terms of which ones did I fill in. And then the same argument can be set here, but it's already pre-filled in this case, so I don't have to do a single thing. This is an AND gate. A is a regular AND AND gate. It is not a NAND gate. So in the case of an AND, if I know one of the inputs is a 0, not knowing anything about the other one, can I conclude what the output has to be? Has to be a 0. Very good. So that is also based on the truth table, but we never really kind of talked about or displayed the actual truth table because that is something you have learned in CISP 360 already, possibly as early as 300 with that one. Okay, so that's a 0. So now we have go for another ANSI. So anytime a PD ends up with any change, okay, if on the PD row there's any items, okay, you have to go for another ANSI. So now we look at this 0 here, and it belongs to node 2. So anything on node 2 should also need to be updated to a 0. So that would be this one over here, okay? So this one is belonging to node 2. I'm just scanning. There are no other node 2. This is a node 4. So anything that is on the node 4 should also update to a 1. Okay, so that one is updated to a 1. This is node 3, but it is pre-filled already. The only thing you really need to be careful is, are we already accounting for all the node 4? And in this case, we are. Is that okay so far? Any questions? Nope. You're good. All right. Well, because the NC row, this entire NC row is not empty, we have to go for another PD because as long as one of the devices has at least one of the input ports changed, we have to kind of redo another PD row. So in this case, this just changed from an unknown to a 0, and as a result of that, Q becomes a 1. This is pre-filled. I didn't put it here, so it's not part of the answer. So that one is accounted for. This one over here is new 2, and as a result, this 0 is now here, and this is also not something that I have to fill because it's already here. And then this one is new. Okay, so this one is new, but we only know that the S input pin of an SR latch is a 1. There's nothing I can conclude because if I only know that the S pin is a 1, that means Oh, not knowing what R is, I really have no idea what the output pins should be. So I cannot make any conclusion whatsoever. So I'm going to leave both the Q and the NQ to be blank in this case. This is also a change, but this belongs to an AND gate. One input pin of the AND gate is now a 1. The other one has been a 0 all along. So the output continues to be a 0, which means I don't have to put anything here. Is that okay? So this entire PD row, um, is handled. Okay, I wouldn't say it's empty, but I did not have to write anything here because the ones that are already provided in the answer is already describing what should happen here. So now we go for another NC row. So this NC row has to kind of mirror all the changes here. This one needs to be propagated to everything else that belongs to a node 5. So here's a node 5. It is now changed to a 1, and that's the only other node 5. So we are good here. This is a 0, but that's okay because this one actually does not have a node number, which means it is not connected to anywhere else in the circuit. So it's quote unquote a dead end. Okay, so I don't have to worry about this one. So now we have, the NC row is all done. Okay, I did not have to fill in a single cell in this case. So this one is still a change to one of the input pins. So as far as SR latch D is concerned, S and R are both ones. But I still cannot make to any conclusion about its output because 1 as input to this kind of a SR latch means maintain the current value of your Q and NQ. Well, I did not know how they started off to begin with, and I still don't know what they're supposed to be. So that's why both of these cells remain empty, because when both input S and input R are ones, Q and NQ are NC in this case, but that NC does not have to do with node connectivity. It is the abbreviation of no change. Very good. Okay. So now we are, okay, now I have to keep track of where we are. Okay, we are on this PD row. It is now completely empty, which means it is the end of one step. So now we start the next step, which is changing G from a 0 to a 1. So this one, is immediately using node connectivity to update every other column that belongs to node 1. This is a node 1. This is also a node 1. It is getting the same one over here. This is also a node 1. It is also getting the same one over here. I don't have to do a single thing, because all the cells are already pre-filled the way they're supposed to. The next row is a PD, propagational delay. So now I know both of the rows or both of the input pins as far as SR latch F is concerned. And with the SR latch, when both inputs are ones, it means it is just preserving the output. So there's nothing I have to put here nor here. Is that part okay? All right. So the other one is over here. Now this one is significant because this belongs to one of the input pins of the AND gate, which is A, device A. Now, at this point, both input pins of the AND gates are 1, so that means the output has to change to a 1. So we do have a change here in the propagational delay. So the next NC is going to look at node 2 and go like, okay, who else is connected to node 2? It should also be a 1 at this point. The only one that is also connected to node 2 is in the first column. So this one is now changed to a 1. All right. Are we still doing okay? All right. So let me just turn this into italic. Oh, okay. That's not what I meant to do. Wrong key. Now I have to go back. I believe it was this one that we were working on. Okay. Was it? Yep. So I turn it into italic. And then now we go for another PD. So at this point, okay, it's good to be able to scroll up. So at this point, SR latch J has S being 1 and R being 0. So we look up the table, we go like, okay, Q should be a 0, NQ should be a 1. NQ has been a 1 all along, pretty much, but Q needs to change from a 1 to a 0. So this 0 was already pre-filled when you got the question, so I don't have to do a single thing. But because of this change, we have to go for another NC. This belongs to node 5, so everything that is on node 5 should also update to a 0. This is the only other column that is on node 5. It is now updated to a 0. So because this is also one of the input pins to SR latch D, we have to go for another PD row again. So at this time, as far as SR latch D is concerned, its inputs are 1 and 0, being S and R. So we look up the table, and we find that Q should be a 0 and Q should be a 1. So Q should be a, where am I? 0. Okay, so this one should be a 0. This is new. And the other one should be a 1, which is already pre-filled, so I don't have to do anything about it. And then after that, we have to go for another NC. In other words, if a PD row is non-empty, you always have to follow it up with an NC row, unless the only thing changed in the PD row does not belong to any node. It is a dead end. Okay, so it does happen in this circuit, but it doesn't happen. You cannot count on it to happen in general. All right, so what do we do? This is a change from the PD. It is on node 6. So now everything on node 6 should change to a 0. So this column is also on node 6. That should be a 0 at this point. And I'm just scanning. I don't see any other node 6 anymore. This one is not affecting anybody else because this particular column has no node number, which means nobody else is going to be changed because of this one. So this is the only thing for the NC. And the next PD row is empty because what we have changed here is H, but H is just an output pin. It is not a device, so it doesn't affect anything else. There's no update after port H or output pin H is changed. So that's why the next row is empty. And then we change the G port back to 0. Okay, so anything that connects to node 1 should also update to a 0. So that would be this column and also this column here. And then then we go for another PD. So now it's going to get a little bit harder to read, if I need to read some of the earlier values. So we have to look at this pin. It belongs to the R port of SR latch F. So SR latch F is now having a 1 for the S input and a 0 for the R input. So we look at the table here, the output should be a 0 and a 1. But it's already a 0 and a 1. So as a result, there's nothing for these two cells because the actual output port values did not change at all. So that's 1. We now look at this particular 0 here, which belongs to an AND gate. Well, guess what? The AND gate now needs to change its output to a 0 because at least one input pin is now a 0 and it had a value of 1 before. So that's a change. Because this is a change on node 2, so now we have to update everything on node 2 to also a 0, which is this one over here. But because of that change, we have to go for another PD row. And now with SR latch J, both inputs are zeros. And because both inputs are zeros, then both of the outputs should be ones. So this is a 1 that is pre-filled, and the other one is all the way up here, which is what we filled, but it is maintaining that 1. So that means we don't put a 1 over here. And that concludes the PD. And then because of this one being updated on node 5, the other column corresponding to node 5 also need to update to a 1, and that concludes the next NC row. And for this NC row, both input pin S and R of SR latch D become 1s, okay, because this is a 1 here. So because it's 1, 1, that means the output should stay put. Basically whatever they were remain the same. So we don't put anything here. So now this entire PD row is empty, which also means the next NC starts the next step. The next step updates here B to a 1. That is on node 0. So the only other item on node 0, the only other column on node 0 is this one over here. So that's why this one is also changed to a 1. So now SR latch J has input being 1, 1, a 0, 1. So the output should be a 1 and a 0. So that means this particular port needs to change to a 0 at this point. Make it italic so it's visible. And as a result of this, we have to spread this change in the next NC row. So everything on node 4 should also change to a 0. So that would be this one. Okay. And this is one of the input ports of SR latch F. So now we have to look at SR latch F and ask, okay, what should be changed in the next PD? If both inputs are zeros for SR latch, both outputs should be ones. So that's why we changed this one, but this is pre-filled from the exam itself, because it's a change from this 0. NQ has always been a 1. So when we need to where are we supposed to be at this point? Uh, I have lost track. Okay, right here. So there's no cell value here because NQ has been a 1 from early on, and now we go like it is a 1 again. Well, if it's a 1 again, it is not a change. If it is not a change, we do not fill in the cell. All right, so this is a change. So in the next NC row, we look at this one, but this one is not a problem because there's nothing here. It does not connect to anything else. So that basically concludes this particular step. And then the next step is starting with this row is changing G back to 1. And as a result, this column is updated to a 1 because they all belong to node 1. And same with this one, it belongs to node 1. And now with SR latch F, we have 0, 1 as the input, and the output should be a 1, 0. And that is so this is a 1, it's already a 1 here. And this one needs to update to a 0 because it was not a 0 before, it was a 1 before. So this is an update, but it's already pre-filled in the exam that you are getting. So you don't have to do anything here. There's nothing to update. And because of the update to NQ of F, okay, we have to go for another NC. So we spread that 0 to everything else on the node 3, which is this particular column and also this particular column. And then we just go to another PD. And the other PD is based on this input being a 0, this input being a 1. In other words, we have 0, 1 for SR latch D. And we have 0, 1 here. The output should be a 1 and a 0. So this 0 is a change from what it used to be because I think it used to be a 1 over here. And then we also need a 1 over here, put a 1 over here because that used to be a 0. So that also needs to change to a 1. And because this is the one that I put in, we'll make it italicized so we can kind of remember. This is also updated to a 0. So this will cause the AND gate to output a 0. So let's see what it is outputting already. It's already outputting a 0. So there's no change to this particular cell. And the next NC is looking at this update and go like everything on node 6 should also update to a 1. The only other thing on the node 6 is this column here. So this is now updated to a 1. And because this is an output port, so it doesn't cause any propagational delay effect. So the next PD row is empty and we are done. So I did not do the shortcut, which is just filling in the column that is missing. I just worked out the entire thing from the beginning to the end. So you can approach this question in two ways. You can look at the values that are provided as some place for you to double check things. So if you make a mistake somewhere and then the provided numbers does not jibe with what you think it should be, then you know, oh, okay, I made a mistake somewhere. Let me go fix it. Okay, so you can use that, for double checking your own answers. All right. So do we have any questions regarding number 1? If you're thinking this is super boring, well, congratulations. That means you have mastered the technique already, and the rest is just tedium. All right, so now we move on to question number 2. Question number 2 says we are describing the operation as the reference C equals to A. So the first part of the question, for 20% of all the scores, you are asked, describe the port connectivity needed to implement the RTL description. This can be in the form of assignment where the left-hand side is the input port and then right-hand side is the output port. For example, the fetch operation can be described as follows. So the D port of the instruction register is connected to the D port of RAM, and then the A port of RAM is connected to the Q port of the program counter. So I'm using this as an example of what format I'm expecting for this particular answer. So you don't even need to reference the circuit for this particular question, because what you can do is to go like, okay, what is A and what is C? They are registers. Okay, so how do I get the value of register A? Which port will give me the value of register A? Okay, let's name all the ports of a register. Okay, so we are going to go in this direction. Okay, so on your left hand side, the first one, the top left port is called the D port, which is an input. Okay, the next one down is enable, and then this one, at the south edge is the clock. This one is reset, and then this one over here is the Q port, which is the output. Okay, so I'm expecting you guys to be familiar with the register ports, at least at this point. If not, have a diagram with you, okay? Because all of those are really available in Logisim. And I'll give you guys a neat trick to print out things from the built-in help of Logisim. You guys will go like, oh, I didn't know I could do that. So I'll talk about that right next to this. Okay, so anyway, the answer to this one is somehow we need something to be updated to A dot Q. Oh, wait. A dot Q. All right. So what is going to be updated to A dot Q? Okay. We are changing the content of a memory location, which means most likely the RAM component is involved. And we are updating, A is used to update the location, update the content of a location in RAM. So which part of RAM should I be using on this side? In other words, this is RAM dot what? So now you have to think about all the ports of RAM, right? So going in the same direction. Okay, so we have the A port over here. We have cell, select, and then we have, cannot remember the next one. Clock. Okay, so we have clock, which is a triangle like this. Is it LD before the reset? Okay, LD and then reset, and then on this side we have D. Okay, so those are all the ports surrounding a RAM component, at least in the processor that we are using. So now you have to ask which one should connect to A.Q in order to update the content of a location. Okay, sorry, go ahead. D, that is correct. So RAM.D should connect to A.Q. Then you go like, okay, what about the other ones? Well, the other ones, some of these do not really have any connectivity to other registers. Like cell is just coming straight out of the ROM. It has to be 1. Clock, we're just waiting it to rising edge. There's no connectivity to specify here. LD has to be a 0 because we are writing to ROM, and then the reset has to be a 0 because we don't want to clear all the content of ROM. So the only other port that has to be specified, like, oh, this has to be connected to somewhere, is RAM.A. So now you have to say, okay, what about RAM.A? Where should it connect to? What is the purpose of the A port? What does it do? Sorry? It specifies the location, right? Okay, very good. Okay, it specifies the address where we want to overwrite the content. In other words, it specifies, okay, so the D port specifies what is the new content. The A port specifies, but which location am I changing? Okay, So using the RTL description here, what do you think should connect to RAM.A? It should be C.Q. The output of register C should connect to the A port of RAM, because according to the RTL, we are dereferencing register C. That is basically what dereferencing means. So, if not for anything else, okay, this discussion should help you understand a little bit more of what is dereferencing in CISP 360, because that's basically what it boils down to. Okay, whatever value is the pointer connects to the A port of RAM in order to specify, oh, which location am I changing? Okay. So that would be the answer to the first part. The second part is a little bit harder to answer without the map to the processor. So what it's asking is for each line of the previous part. So we got two lines in this case. List all the relevant tunnels that contribute to the routing from the output port, which is A.Q and C.Q, to the input ports, which is RAM.D and RAM.A in this case. The ordering is not important, okay? And I cannot spell important, it becomes impotent. Okay. This list is limited to tunnels at the top level of the processor. There's no need to specify names that are internal to the register bank or the ALU. All right. So once again, these are examples, and these may not be correct. So this one is basically saying in order to route RAM.D to instruction register.D, these are the signals that are involved. Okay. It may not be correct. It's just an example of the format of your answer. Okay. So take this only as a clue of what the format of the answer should look like. So what I'll do is I'm going to copy this. Okay, obviously you cannot copy and paste on the paper, but I'm just doing this so that I remind myself which parts I need to answer. Okay, so I handle each route separately. So the first question is, how do I route A.Q as an output to RAM.D as an input? I cannot answer that question without a diagram. So let me go ahead and start up Logisim. So what this means is if you are answering these questions, unless you have a photographic memory, you probably want to have the map available to you like this. Okay. I already gave you guys a PDF that includes the processor, the ALU, and also the register bank on a single page. Okay. So you are responsible to bring that with you. Okay. When somebody in the class, next Tuesday and go like, I forgot to bring mine, I go like, that's not much I can do. Okay. So make sure that you bring the map with you. Okay. Now the map that you're bringing with you can have highlighting. It can be color coded with all the routes and whatnot. Okay. So do what you can to annotate the rather boring black and white picture with highlighting, annotations, and whatever you think can help you, answer this kind of question. All right. So I will refrain from actually clicking on the note, because that would be cheating, because that gives me an advantage of working with an interactive tool. So let me go back to the question and focus on just this question here. How do I route A.Q to RAM.D? A.Q is coming out of the register bank. It can be coming out of either one, okay, out 0 or out 1, and I honestly cannot remember which one it's coming out of, but that's okay, which means I can also start with the other end, which is RAM.D. So I start with RAM.D, which is right here, and I'm refraining from clicking on it, okay, so I don't have the added advantage of having the wire already highlighted, but you can pre-highlight using a color, okay, on your sheet. Okay, so that's what I'm basically talking about, is if I can do this with an interactive tool that gives me a visual advantage, you can do the same by highlighting that entire node with a particular color. Okay, so you can get, like go to the Dollar Tree, get a bunch of highlighters of different colors, and just go wild, on that map. Is that okay? So these are the things that you can actually do. And by the time you're done with highlighting, coloring all the routes and whatnot, you are already gaining a certain level of familiarity with the circuit because you have to kind of follow it, right? It's like, oh, where is it going? Oh, it's going over here and then drop down over here. So by doing that, you're already quote unquote studying. Okay, so now this is the D port. I needed to go to one of the registers. So so at this point, it splits into two. Okay, so out down here, that's not what I need because I need to route it to the output of one of the registers inside the register bank. So that means I will follow it here. Okay, and then it goes all the way up here. It is coming out of this demultiplexer. Oh, okay. So this demultiplexer outputs to the D port of RAM, but it's getting its input from out 0 of the register bank. That sounds like what I need. So in order to um, specify this route here, I need a few things. I need register output 0 enabled to be a 1. Okay, so I'm gonna kind of flip back to the other side and mention that register output 0 enable, and I already know it has to be a 1. So even though this question does not ask about the value, it doesn't hurt to include the value now that I know what it is supposed to be. But in order for this demultiplexer to output 2, I also know that register output 0 demux needs to be a 2. So I will also make a note of that. Register output 0 um, demultiplexer needs to be a 2. Now, whether you want to write 2 as a decimal number or 10 as a base 2 number is kind of up to you. I would use base 2. Okay, I would use base 2 numbers, just because when we're working with the tunnels in the processor, most of the time we need to kind of drop down to binary. All right, so what else do we need? I think that's it. Okay, so these two are the only ones that I need in order to route. Oh, wait, there's one more, because in order to specify that particular register, register output 0 cell also needs to specify the register. So register output 0 select also need to indicate register A, and that would be 0, 0 in base 2. Okay, so I'm just going to pause here and see if this is all okay with you guys. Yes. So this is just connecting, finding out what output or where output is coming from, like RAM.A and RAM.B, like where is it leading to? I would describe this as finding out what tunnels are needed in order to route, in this case, in order to route the output of the register A to the D port of RAM. That's how I would describe what we are doing. Is that okay? All right, okay. So I think that's it for this one, okay? And then for the next one, we have to somehow route the output of register C to the A port of RAM. So I go back to the picture, but this time I'm tracking down the A port, and I say, okay, this has to go back to the register bank somehow. So I track this wire, okay, track it. Ah, it's coming out of a multiplexer. So now you have to say, but which input of the multiplexer do I need? Well, input 1 goes to the program counter, not what we want in this case. Input 0 kind of goes through another multiplexer, but it does come out of the register bank. That seems to be what we need. So we need ADDR mux to be a 0 in this case. So I jot it down. ADDR mux needs to be a 0. And we know this demultiplexer is in the way too. So that means in order for this to be connected to this wire over here, we need the select of this demultiplexer to be selecting 0. So that's the job of register output 1 demux. Register output 1 demux needs to be a 1. And this is coming out of out 1. But what is coming out of out 1 is selected by register output 1 select. And because we need register C in this case, so register output 1 select needs to be 10. Very good. There we go. All right. So yes, can I go back to Logisim? Oh, you mean this one? Yes, it should be a 0. That was my bad. Thank you. Good catch. Excellent. Are we good so far? Okay. All right. So that is part 2. So far, if I got all of these answers right, I would have gotten half of all the points for this particular question. So part 3, it gives you a table and it's asking you to fill in all of these names. So no cell should be empty, okay, especially for the value part. The reason part, you can probably reuse some of the reason over and over again. So now we have to kind of start from the beginning. rom.d 0, which is bit 0 of rom.d. This is rom.d here. This is 0. It is connected to the enable of the instruction register. So that has to be a 0. Okay, so we'll just say that the instruction register is not being updated. RAM cell needs to be a 1 because we are writing to RAM. Okay, so we need to use the RAM. Okay, using RAM is, I mean, you don't have to give me like a 2-paragraph write up on every single cell of the reason. Just something that explains why it has a value of 0, why it has a value of 1. That's enough already. RAM load in this case should be a, we are overwriting RAM. So what is RAM load? Should be a 0. That is correct. So we are basically we are saying you're writing RAM location. That's the reason why RAM load is a 0. RIMux is not care. Okay, question mark, because we are not updating any register. And then RIEN has to be a 0. Okay, so once again, this is not updating any register in the register bank. RISEL, once again, is a question. Oh, these have to have the same width, for the tunnel. So I think this is a single question mark. This is a double question mark, because RIMux. If I go back to the circuit, RIMux is a single bit, because RIMux is right here. It is a single bit to select one of the 2 inputs. So that's why it is a single question mark. RISEL is 2 question marks because we need 2 bits to specify one of the 4 registers inside the register bank. So the number of question marks has to be correct as well. Otherwise, points will be deducted. Okay. If you give me a single question mark when double is expected, you're not going to lose all the points, but you will lose, like, it will turn an A to a B, basically, a 4 to a 3. All right, so register output 0 enable. Okay, if I remember from the previous one, this has to be a 1 because we are, oh, this one is saying, okay, not update any register. This one needs to be a 1 because, register output 0 is register output 0 connects to, I think this is the D port, ram.d. And the select is 0, 0. Because we need to specify register A in this case. Demux, okay, this one I cannot remember, is 1, 0. Okay, so we'll put a 1, 0 here, and we'll say output 2 connects to ram.d. Register output 1 select has to be a 1, 0 because we need to specify register C, and the demux needs to be a 0. Okay, whoops. Okay, not that. Put a 0 here because we need output 0 ultimately connects to ram.a. ALUEN is a 0 because we are not performing ALU operation. ALU op are 3 question marks for the same reason. We are not performing any ALU operation. Address mux, I cannot remember but that's why I wrote it down a little bit earlier. It's a 0. So we put a 0 here. So we basically say we need to connect from register bank to RAM.A. That's the reason why it's a 0. PC mux is question mark, question mark, question mark, because we are not updating the program counter. PCN is a 0, not a question mark, because we are not updating the program counter. So bit 24 and bit 25, those two I cannot remember, so I'm going to have to look up. All right, so bit 24 is this wire. It connects to the select of the multiplexer that feeds to the D port of the microcode pointer. We want it to increment, which means it needs to be a 1 in this case. So we put a 1 here in order to increment the microcode pointer. And I believe this one needs to be a 0 because we are not resetting the microcode pointer. Because if I go back to this circuit here, bit 25 is this wire. It goes to an OR gate, and then the output of the OR gate goes to the reset of the microcode pointer. We are not ready to clear the microcode pointer yet. All right, so that's the complete answer to question number 2. Do we have any questions about the answer? Okay, you first and then you. Go ahead. Hmm? It is explained in the question. So in the question for part 3, it says, in the value, this should be a binary number corresponding to the width of the signal, meaning that even for value 0, it should be denoted as 0, 0 if the signal can be anything for the specified operation. If the signal can be anything for the specified operation, then use question mark as the value. The number of question marks should match the width of the signal. So does that answer the question? Okay, is your question about the number of question marks, or is it about why use the question mark? Because it would not matter. You can, okay, so I'll give you an example. Because we are not updating any of the any one of the 4 registers in the register bank, so it means you can specify 0, 0, 0, 1, 1, 0, or 1, 1. It would not have made a difference. Correct. Yep. But we cannot use a question mark for RIEN because in order to make sure that none of the 4 registers are going to update, RIEN has to be a 0. Is that okay? All right, so your question. Mine was actual finding the values and reasoning. So do you recommend for the exam to have the actual on a piece of paper? Yes. And just look at that to find the answers. Just like what I did. Yes. I already gave the class a PDF of the 3 circuits that are relevant. If you think that is a little bit too small, you can also kind of do whatever you want. Okay, just do whatever you want. But there are you cannot use a computer, nor a tablet, nor a cell phone during the test. So does that answer the question? Okay, all right. All right, so question number 3 of this exam does not apply to us because it's a floating point question, which we already answered in exam 1. So unless the class unanimously say, but we want another question on floating point numbers, in which case I can give you another one. It's okay. I don't mind the slight extra work. So unless it is unanimous from this class, we'll just go like, we're not going to do floating point this time. Is that okay? Is anyone dying to do floating point in the exam again? Okay, seeing none, we'll just skip this one. Okay, so now we move on to the 3rd question that is not in the previous semester. Because of the reason why that is the case is because I reordered the topics a little bit. So that's why we have a different kind of question number 3 this time. So that is in the announcement. I hope people are at least reading the announcement once in a while. So I save this as filemin3.zip. It's going to overwrite the file that's already there, which is fine. And then I switch to a text editor. Okay, so there we go. And let me maximize this because the more space I have, the better. Is the text size okay for people who are sitting in the back? Is that readable? Okay, all right. So I'm going to unzip this. Obviously, you don't have to do this. I will provide all the information that you need on the printed portion of the exam. Okay, so you don't have to do any unzipping. But because I didn't have time to actually put it on quote unquote paper, which is PDF in this case, that's why I just kind of got this. So find min3, okay, it has two files. One is find min3.c, which is telling you what the code is supposed to do, and one is find min3.ttp-asm, which is a faulty implementation of the C code. All right, so this is what it looks like in my editor. In the test, there will be no syntax highlighting on the assembly code, so you cannot immediately identify, go like, oh, that's your pink color thing, something is wrong with it. Okay, so there will be no visual cue of what may be wrong with the code. So you're gonna have to eyeball the whole thing. All right, so this is the C code. The C code basically just says, we have 4 unsigned integers, A, B, C, D, as quote unquote variables. This is the code. I know this is not compiled in C because it is not inside a function, but because I don't want to throw function into the exam either, so we'll just go like, okay, we'll just work with registers, not within the context of a function. Is that okay? So all we want to do is to implement this code over here. And on the other side, I'm forgetting one thing at the very end. Oh, okay, I did remember. Okay, never mind. So the C code is just like this. So now you have to remember the processes in order to break down the C code into the most elemental C code that uses like if something, go to something. Okay, so that is in the compiling module. Let me point out which module we are talking about so that when you are studying, you know where to find that information. So we are talking about this module here, compiling C control structures. All right. So depending on how good you are, with breaking down the C code into assembly code, you can consider doing this really step by step, or you can just eyeball the whole thing. Okay, so it's up to you. The original C code says, if A is less than or equal to B and A is less than or equal to C, we want to copy register A to register D. Otherwise, go do something else. Okay. So if you remember the compiling code thing, we're always looking for an excuse to go to the else case in the case of an if then else. So that means, we are, assembly code, we compare the two registers, and then we are looking for a reason to go to skip over to the else case. The question is, are we skipping correctly in this case? Okay, so then you have to ask yourself, what are we supposed to do? Okay, so in your answer sheet, you can always add as much comment as you want. Okay, all right, so it is not just a hint, this is actually a recommendation. Okay, because if you don't put in the comments, you may not be able to track what the code is supposed to do. Okay, so I would put in this code here just so that I can keep track of what I'm supposed to do. So basically, I would say, okay, what we really want to do is if A is not less than or equal to B, then we have a solid reason to go to the else case. But this is really the same thing as saying A is greater than B, go to else 0. But the only thing I can really check for is when B is less than A. Okay. All right. So these 3 lines of code are really equivalent. They're all giving me one of the 2 reasons to go to else. Okay. So you look at this and go like, okay, if I have compare BA, JLI to else 0, does that do what line 12 is suggesting? The answer is almost, with one problem. It's using the wrong flag because it's supposed to be using the C flag and not the L flag. So I'm gonna change it to a C flag over here. Come on, C changed from JLI because we are dealing with unsigned integers. So the C flag is good for unsigned less than, the L flag is good for signed less than. That discussion was in binary comparison, which is right after binary subtraction. Okay, so in case you guys are wondering, where did we learn all this stuff? That's when we learned it. Okay, um, I take it back. Binary comparison is not right after binary subtraction. It is right after signed versus unsigned. So those are the modules that you might need to go back to review if you're looking at this and go like, I have no idea why we are changing JLI to JCI. Okay. As to the pattern of why if B is less than A go to else 0 translates to line 13 and 14, that is in the compiling C control structure module. So I can point out exactly where that is too. So I believe that is down, 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 the way right here. So this is the section that basically says if this is a L or less than, then you have to use less than over here. But less than in unsigned is the C flag, less than in signed is the L flag. So that was that entire discussion. Even an example right here. Okay. If this looks a little different from the last time you looked in this module, that is, you're correct, because I actually added syntax highlighting to this whole thing, and that's why it looks a little bit different this time. So you can see how later on, with all the actual expansion of the assembly code, it is actually syntax highlighted. Not that anyone cares, but I do. Anyway, all right, so that is fixed. And for the same reason, this also needs to be fixed because we have two reasons to go to else. Because it is possible that B is less than or equal to A, but if B is not less than or equal to C, we still want to, oh, I take it back, sorry. So if A is less than or equal to B, okay, but A is not less than or equal to C, we still want to go to the else here. So that's why there are two reasons to go to else 0, which is corresponding to the else of the outermost conditional statement. Okay, let me ask you this question. How many conditional statements do we have in the C code? So look at the left-hand side. How many conditional statements do we have in the C code? I'll give you 2. That is correct. Okay. The next question is, how are these 2 conditional statements structured? Is one right after the other one, or is one nested in as a part of the other one? So that's a trick question, okay? It is a trick question because visually it does not tell you the right answer. Let me repeat the question again. We have 2 conditional statements. Is one right after the other one? In other words, they are independent, okay? They're just sequenced one after another. Or is one nested as a part of the other one? The answer is one is nested within the other one, okay? Because you have to look at things from the compiler's perspective. The compiler see this else and go like, oh, this else is corresponding to this if. Not a problem. We see that too, right? But after the else, the compiler says, give me one statement. Okay? Without curly braces, it can only take one statement. But guess what? This is that one statement. I have to do it on this side. This is that one statement. So that means what is highlighted in gray right now is actually nested as the only statement for the else of the outer conditional statement. Is that part okay? Okay. So that means from the structural perspective, the C compiler actually see it like this. There's an implicit curly brace here, and there's an end curly brace all the way down here. So from that perspective, I think now you can see why line 9 to line 16 is a conditional statement that is apart, nested as the else branch of the outer conditional statement. Is that okay? Now, this is not a compiler class, and yet I still need to talk about the syntax of C++ because this is something that you should have some exposure to in CISP 360. Now, how explicit your professor made this clear is not something that I can tell, but I can tell you this is important. Okay, this is actually very important. All right. So knowing that this is how the program is structured, else 0 as a label is corresponding to exactly where the blinky cursor is. It's what shall I do if the condition of line 4 is false? Is that part okay? All right, so I named the labels based on the structure of the code, and I would not give you a wrong label name to lead you to believe something other than what the structure of the code is suggesting. So I'm not going to mislead you with labeling incorrectly. That would not be, at least not in this class. Is that okay? All right. All right. So now we got that fixed. So this one has the same fix over here. And we say changed from JLI because we're dealing with unsigned comparison. Okay. All right. Well, line 17 is pink. I think that tells you that something is not right with it. This is what we want to do in C. What should I use in assembly code? So we got a family of instructions that mention 2 registers, and they're good for copying stuff. So one is LD, one is ST, and one is CPR. Which one should I use? CPR, very good, because we are not dealing with memory whatsoever. We are just copying a register to another register. So this needs to change to CPR. So changed from, I think, LD, because we are just copying registers. We are not changing or reading memory locations whatsoever. Okay. All right. So this is a JMPI to end if 0. Let's check out where end if 0 is right here. Looks good to me, because if you have a if, else something, as long as you take one of the branches, you're done. Okay. After one branch, you go all the way to the end, which is right here. Okay, that seems correct. And then we have else 0. So once again, else 0 is corresponding to exactly this point here. If the condition of line 4 is false, what am I going to do? Well, there's another conditional statement. So we start with comparing again. So this time we want to find a reason to go to this particular else here, which is labeled as else else. Why do you think it is called else else? Because it's nested. Because it is the else branch of the else branch. Is that okay? So the label names contain a certain clue as to which part of this code is in the original C code. So you can try to utilize that clue to help you understand, okay, so where are we in this C code again? That's where. All right, so now we basically say, but what am I supposed to do? Well, we're supposed to go, if this condition is false, we want to go here. In other words, if I want to go to else else, the reason why I need to go to else else is going to be if not b is less than or equal to a, go to else else. And the other one is if not b is less than or equal to c, go to else else. Well, okay. This is an and, okay? Or the original condition is an and, but we have to negate it first. We have to basically say if it's not, okay, then we go to else. But then, if you say it is not, the conjunction of b is less than or equal to a and b is less than or equal to c, it becomes the same thing as it is not b is less than or equal to a, or it is not b is less than or equal to c. Is that okay? All right. So we are looking for reasons to go to else else, and these are the 2 reasons. And once again, okay, we apply a little bit of simplification here. And then we go like, but we cannot find out whether something is greater than, but we can find out whether something is less than. Okay, so we have to flip the direction and flip the comparison. Same over here. Okay, this doesn't look like what we are supposed to do. So we have to flip the A and the B. So A and B need to be flipped. Okay, so we say BA flipped to AB because we are looking for um, because we are looking for A is less than B. There we go. JCI is the right flag to use, so we are good there. Over here is the same, okay, because we want to see whether B is less than C, but compare BC is doing exactly the reverse, so we have to change that. So CB over here, so BC flipped to CB because we are checking for C being less than B. All right, CPR is the correct thing to do. Oh, look at this. It's pink. So what is wrong on this line? JMPI, exactly. So instead of JMP, we should be using JMPI. Okay, so put an I over here. Explain, right? JMP should be JMPI. And if you don't give me a reason in this case, it's fine. Okay, I'll just take it that you already understand that JMP and JMPI are two different instructions. And in this case, we should be using JMPI and not JMP. Okay. All right. One last thing. This is the else, which is corresponding to this branch here, is supposed to copy register C to register D, but we already know what instruction to use in this case. Okay. We already know that this is supposed to be CPR. So we go like, ST should be CPR to copy register. There we go. And that concludes this portion of the question. This is basically question number 3. So do we have any questions about the answer to this question? Or what you need to study to do this? Yes. You need to know all the opcodes. You need to understand how to compile code. Now, exactly how you can get that knowledge in your mind, I cannot answer that question because we all learn a little bit differently. But what I can say is all this information is already discussed in the lectures and also in the notes and also in the labs. Yes. We are not going to go to functions, so no need to worry about calling and returning, but the stack can still be a part of it. Okay, we can talk about the stack without calling and returning. Yes. The left-hand side is the C code. It specifies the logic we are trying to implement. The right-hand side is the assembly code, and it is going to be faulty. And your job is to find out what's wrong with it, explain to me why it is wrong, and fix it. In the exam, it will be exactly like this, except it's on a piece of paper. The C code will be given. The faulty assembly code will also be given. Then you'll be using your pen or pencil, cross out some line, you fix a few characters, explain to me why you fix it. Yeah, question? Sorry? Absolutely. Anything on paper is fine. So you can either hand write everything, which I think is not a bad idea, okay? Because if you're handwriting, the whole process of handwriting is quote unquote studying, okay? Because if you're just copy and pasting, okay, let me go to the spreadsheet. Let me see, opcode table. So this table you can just print it too, okay? If you want to, just do a Control P, specify what printer, and just print it out, okay? You can do that, okay? But that may not be as helpful, in terms of studying. So if I was studying for this class, okay, and I have time, I know some of you are taking a lot of units and you may be pressed for time, okay? So you have to kind of gauge how much time to spend to study for this class, because I know you got other classes too. But if I were to study for this class, the way I would do this is to kind of handwrite everything on a piece of paper. I would put all the related opcodes together along with their RTL description. Okay, what is RTL again? Very good. Okay. I'm impressed now. Okay. But I would group them together because grouping in your mind, okay, categorization, grouping, and activities like that involves the analytical part of your mind, because you're looking for similarities and differences between things. That is studying. Okay, it is exercising that critical thinking part of your brain, of your mind, and that's studying. So, just casually, I'm going to say there's a whole bunch of stuff that performs copying. Okay, so we have LD, ST, and CPR. They're basically copying things around. Okay, so they kind of belong together. So I group these together. There's JMPI, okay, which is changing the direction of execution. But there are also conditional branches like JCI, JSI, JZI, JLI, and then JOI. So these belong to a particular family because even though one is non-conditional, the other five are conditional. They still kind of accomplish sort of the same thing, right? Because they can alter the path of execution. And then we look at things that are related to addition and subtraction. So they belong to yet another family. So subtract and compare, these two are very much related, okay? Because the only difference, if you look at the RTL, the only difference is what do we do, or do we even bother to do anything with the difference, okay? One doesn't do anything about the difference. It's like, okay, we'll do some calculation, but then that's it, okay? The other one goes like, oh, wait, I have to store that difference back to something. Which one is which? I'm not going to tell you because you can see it from the RTL description. And then we have other instructions that also go through the ALU, like add. We really do not talk much about we also use and, okay? And is important because and, as opposed to or, allows you to specify the same register twice. So you can have and AA, which does exactly what and AA suggests that it would do. The importance of AND AA is it is forcing the value of A as a binary number through the ALU and therefore changing the flags. Okay, we know for sure that the Z flag and the S flag will be affected. Okay, so keep that in mind. Okay, so AND is kind of special. OR is, we haven't really used OR yet. Okay, it's kind of doing the same thing, but OR AA does not exist. Okay, it does not do what it thinks, what you think it does. Compare AA also does not do what you think it does. Okay, so we got OR, and then we got right shift, which we never really used at this point of the class. We used not once, okay, in one of the labs. So these are, I think, one family because they all go through the ALU and they can all change at least a few of the flags register. So typically, these 5 instructions would be meaningful unless they are following one of these. Does that make sense? Okay. And then out of these, we also have increment and decrement, which is kind of an affiliated member of this group, but yet they are distinct because increment and decrement intentionally do not change the flags register. And all they do is to add one or subtract one from a register. Okay, so they are really handy to use in many cases, and there are reasons why they do not change the flag register. So I think, oh, okay, there's another family, okay, no op and halt kind of goes to yet another family here. No op doesn't do a single thing, okay, yeah, so it really doesn't do anything. It doesn't belong anywhere. Halt is, well, when we get to the halt instruction, the entire program stops executing and it's not going to proceed any further, okay? So I think this is how I would categorize the instructions into their own little families, and then for each one I would kind of use RTL to describe what it does. And when you fill in your notes, the paper that you want to bring to the class, you can do it one of two ways. Okay, you can write down all the RTLs, and then you try to remember which instruction performs that particular RTL, or do it the other way around. Okay, do it like this, and then you go like, okay, what is the RTL of load x in parentheses y? So now you have to think about, okay, it is x equals to asterisk y. Okay, because that process helps you remember and also differentiate between these instructions. Yep. Absolutely. Yep. Go ahead. I'm just. But if I were you and I have enough time, I would try to come up with this list because it's also basically testing. Do I remember all the things that we have introduced already at this point of the class? Yep. So taking a picture is good as a backup. Exactly. That would be the best way to do it. Yep. All right. Um, I don't know what else to say. I mean, I can give you guys suggestions of how to study, but I don't know how your mind works, so I can't really tell you exactly how to do it. Hmm? Um, okay, well, thank you. I guess. But different people really learn differently. So, I can only say, well, this may be helpful to you, but it may not. Okay, because some people are less visual and they're more auditory. So for auditory people, they need to listen to the lecture again. Okay, because they get most things in through auditory channel. And I'm very bad with auditory learning. I cannot listen to books, you know, audio books, they don't work on me, because by the time they get to the third sentence, I would have lost track of the first. It's like, what is the context of this again? All right. So anything else? I mean, just remember you can bring paper with you. Okay. That's really a big plus. Okay. And there's no limit either. Okay. If you go to the lecture recording and you go like, oh, this screenshot is exactly what I want. Well, pause the screen in YouTube. I know you guys know how to, do a screenshot and just cut out the portion you want, paste it on the document, print it out, and bring it with you. Are we good so far? There's no limit. The only okay, so the caution before someone decides I'm gonna bring a little hand truck to bring all the paper that I want to bring with me is the more you bring in, the more difficult it is to find the one that you need. Okay, so that means printing out all the modules is good as a backup, but don't use it as your primary source of information. The primary source of your information should be a lot more concise, because the reason why my notes, my modules, is not good, suitable, for an exam, is because the way I write is to explain why things work or how things work. So that's why there's a lot of there are key points that you need to understand, and there's a lot of reasoning in between, a lot of derivations, reasoning, and whatnot. So in the exam, you don't need as much of the reasoning. The reasoning is good when you're studying, but not when you're in the exam. So your notes can be far more concise than the modules that it's already linked from Canvas. That makes it easier for you to find the information. So that's the only caution that I have. When you said, "Oh, there's no limit," yeah, that is correct. There is no limit, but there's a downside of bringing too much with you. So you can always prioritize and just go like, okay, these are the most important ones at the top. These are kind of like the backup, just in case I need to drop back to the original document. And then these are really just supplemental stuff. I probably don't need those, and just keep it in a separate binder. All right. Anything else? So the recordings, the lectures are recorded. If I even if I don't record on the Tuesday, Thursday, the same lecture would have been recorded on the Monday, Wednesday. So you can always check out the Monday, Wednesday lectures as well. So other than that, I really don't have anything else to add. All right. Well, I don't have a lab today because we have not covered any new material for the next lab, but I will stay here for as long as there are people here to ask me questions. So think of this kind of like an extended office hour. Uh-oh. What just happened? Oh, screensaver.